Dear students, welcome to a new lesson. Water is an important part of our lives, isn't it? When we feel thirsty, we drink water. What do we do during hot summer seasons? We drink water mixed with ice. When we get a bad cold, we inhale vapors of water, sometimes mixed with some medicines to clear our nose, right? In each of these instances, we use water, but in different forms, correct? So, water can exist in different forms. Below 0 degrees Celsius, water is a solid. Between 0 and 100 degrees Celsius, water is a liquid. And above 100 degrees Celsius, you know that water is a gas. So, the state of matter depends on the temperature in which water exists. And each of these states has unique properties. Not only water, but different substances exist in different physical states. Say carbon monoxide, carbon dioxide and oxygen are gases at room temperature. Water and mercury are liquids, whereas most metals are solids at room temperature. Thus, all substances can exist in any of the three physical states, namely solid, liquid and gas. And these are called the three states of matter. In this lesson, we will focus on the solid state of matter. Let's see the characteristics that distinguish solids from other states. You might have noticed that solids occur in different but definite shapes. Why do solids have definite shapes? To understand this, we need to check the particles that constitute matter. The constant particles in any matter can be atoms, ions or molecules. As you know, atom is the smallest indivisible part of an element. Molecules are particles that are made up of two or more atoms, and ions are particles that carry charge. Positively charged ions are cations and negatively charged ions are anions. In the case of solids, the constant particles, that is atoms or ions, are held together by strong intermolecular forces of attraction, and they are closely packed. Atoms and ions occupy fixed positions with respect to each other. And if the atoms have to move away, they have to overcome these intermolecular forces of attraction. But is it an easy task? No. To overcome the forces of attraction, atoms need energy. But they do not have enough thermal energy to overcome these forces of attraction. So, the constant particles cannot move and they stay in their fixed positions. Hence, solids have definite shape and volume. Now, let us do an experiment. Let us take a syringe and fill it with a solid, say chalk powder. Now, if we move the piston inwards, what happens? Will the chalk powder compress and come out of the syringe? No, it won't. This means that solids are incompressible. But if you fill the syringe with a liquid or a gas and repeat the experiment, we can see that they come out of the syringe from the other end. Why? This is because liquids and gases are compressible. But why are solids incompressible? This is because the constant particles in solids are closely packed, and there are no more space for the atoms to come closer even if we push them closer. This makes solids incompressible and rigid. Since a large number of atoms are arranged in a small volume, solids usually have high density compared to liquids and gases. Since they are incompressible, rigid and has high density, solids usually have good mechanical strength also. Now that you have understood the characteristics of solids, let us consolidate their features. The constant particles of solids are closely packed and are held closely by strong intermolecular forces. They have definite shape and volume, high density, small compressibility, and they are very rigid. They also possess good mechanical strength. Now, are all solids of same kind, or are there different types of solids? There are different types of solids. Based upon the atomic arrangement, the degree of order in the structure, binding energy, and physical and chemical properties, solids are classified as crystalline and amorphous. As you can discern from this picture, crystalline solids have a definite orderly arrangement of constant particles throughout the three-dimensional arrangement of its structural units. That is, they have a well-ordered and definite geometrical pattern. This ordered arrangement exists over large distances. Thus, we say that a crystalline solid possesses long-range order. Crystalline solids have an arrangement of particles which are regular and periodical. But this gives rise to an internal structure consisting of several kinds of lattice planes, each having a characteristic arrangement of particles. To understand this, let us consider a solid substance made up of two types of ions, for example, sodium chloride, which consists of sodium ions and chloride ions. Let us start from a point in this arrangement of ions and move in the horizontal direction. We will encounter two different types of ions, that is sodium ions and chloride ions in this direction. But if we start from the same point and move diagonally, we will encounter same type of atoms, say only sodium ions or chloride ions. Now, if you measure any physical property of this solid like thermal conductivity, mechanical strength, refractive index or any other optical property, you will get different values when measured in these two directions. This property of a solid is called anisotropy. Thus, crystalline solids are anisotropic. On the other hand, amorphous solids do not have a complete orderly three-dimensional arrangement of its structural units and hence no definite geometry. But they may have some ordered arrangement but existing only in short distances. So, we say that amorphous solids have short range order. An amorphous solid in fact resembles a liquid in the sense that they do not give different values of physical properties in different directions. If you move in different directions, you will encounter same kind of atoms since there is no regular arrangement of atoms in amorphous solids. This property of amorphous solids is called isotropy. Thus, the quality of a material exhibiting different values for a physical property when determined in different directions is referred to as anisotropy. And what do we call such materials? They are called as anisotropic. So, what are isotropic materials? Isotropic materials do not exhibit different values for a physical property when determined in different directions, and this property is called isotropy. Now, let us do a comparison of the characteristics of crystalline and amorphous solids. As we discussed earlier, crystalline materials have an orderly arrangement of atoms, definite geometry and long range order, whereas amorphous solids do not have an orderly arrangement of atoms, no definite geometry and they have short range order. On heating crystalline solids, they melt completely at a particular temperature, that is, they have sharp melting points. But amorphous solids melt over a wide range of temperature. Because of these properties, crystalline solids are called true solids. But if an amorphous solid is heated slowly, it first softens and starts to flow without undergoing a definite and abrupt change. Amorphous solids are therefore regarded as liquids at all temperatures and therefore they are called supercooled liquids. Crystalline solids have good conductivity unlike amorphous solids. They hold their shapes against mild bending and compressing forces, while amorphous solids are easily distorted. Crystalline solids give clean surfaces when cut by a sharp edged tool, unlike amorphous solids which give an uneven surface. And you have already understood an important difference between these two types of solids. That is, crystalline solids are anisotropic, whereas amorphous solids are isotropic. Sodium chloride, sugar, diamond, sulfur, minerals like galena, quartz and pyrite are crystalline solids. Glass, rubber, plastics, resins, coke, etc. are amorphous solids. The next question is whether we can convert an amorphous solid to crystalline. It is observed that there are substances which can exist both in crystalline and amorphous forms. So, yes, we can convert a solid from amorphous to crystalline state. This can be done by heating the substance, melting it and cooling it under controlled conditions. Intermediate states between these two are also possible. Now that you are familiar with crystalline solids, let's study more about crystals. But before that, have you seen a crystal? What is a crystal? A crystal is a solid entity whose structural units are arranged in a well-ordered, regularly repeating geometrical pattern. Now let me ask you a question. Can you prepare crystals on your own? Of course you can. Most probably, you might have prepared it in your lower classes. You might have done an experiment of growing copper sulfate crystals in the laboratory. Preparing crystals is a simple process. To prepare crystals of a salt, dissolve the salt in a solvent and make a saturated solution. Then filter the solution and heat the filtrate. Then allow it to cool undisturbed very slowly at a uniform rate to obtain crystals of the salt. Large transparent crystals of sodium chloride, lithium chloride, silver chloride and many others can be prepared by melting these solids and then allowing them to cool. Let's now discuss about the size of the crystals formed by this method. The size of the crystals depends on the rate at which it is formed. It is seen that if the rate of formation is slow, you will get bigger crystals. Why? Because the molecules and atoms that make the crystals need time to find their proper positions and arrange themselves in the crystal structure. The science of crystals is so developed that we have a branch of science itself called crystallography. Crystallography is a branch of science which deals with the geometry, properties and structure of crystals. Crystallography is based on a group of fundamental laws known as laws of crystallography. One of these laws is the law of constancy of interfacial angles. Another law is the law of rational indices. We will try to master the law of constancy of interfacial angles first. This figure represents a crystal. Each crystal is characterized by faces, edges and angles. The bounding surface of a crystal, which are generally flat, are called faces of a crystal. The line joining the intersection of the two adjacent faces of a crystal is called an edge. The angle between the adjacent faces of a crystal is called an interfacial angle. In 1666, a scientist named N. Steno stated the law of interfacial angles based on his observations on a set of quartz crystals. The law states that the angle between the corresponding crystal faces remain the same for a given substance no matter how the faces develop. That is, a substance can crystallize under different conditions to have crystals with variable size. But the angle of intersection of any two adjacent faces will always be the same. So now, can you guess the importance of this law in crystallography? According to this law, interfacial angles of a crystal type will remain constant whatever be the size and shape of the crystal. So, by measuring the interfacial angles, a crystal can be identified. In fact, determining the interfacial angle is a crucial factor in determining the type of crystal. Let us now move on to the crystal structure. As you can visualize in this picture, the crystal is made up of a number of units. The structural unit of a crystal is called a motif or a basis. A motif is a group of one or more atoms located in a particular way with respect to each other and associated with each point. Now imagine that we are replacing these motifs of the crystal by a point located at its equilibrium position. This is to simplify the whole crystal structure so that we can understand it better. what we get is a periodic three-dimensional arrangement of points. This is called a space lattice or crystal lattice. Thus, a crystal structure is obtained by adding the crystal lattice and motifs. So, what do you understand by the term space lattice? A space lattice is an array of identical points showing how the constant particles, that is motifs of a crystal, are arranged in different sites in three-dimensional space. These points are called lattice points. This figure represents two different lattices with different arrangement of points in space. Please note that a lattice can be one-dimensional, two-dimensional or three-dimensional. To summarize, when an atom or identical group of atoms is attached to every lattice point, we obtain a crystal structure. But you should remember that the points that we have considered are imaginary. Hence, the lattice points are also imaginary. But the crystal structure is real, because in a crystal, each lattice point is occupied by a real motif. The resulting array of motifs is also real. To understand the crystal structure better, let us divide the space occupied by a lattice into smaller repeating blocks or cells. We do this such that these repeating units generate a three-dimensional lattice. Such a repeating unit is called a unit cell. That is, a unit cell is a fundamental building block of a crystal lattice. The lattice points are located at the corners of a unit cell, but they can also be located at the center of the unit cell or the faces. Now, imagine such unit cells arranged in all the three dimensions. Now, we get a complete crystal structure which we call as a space lattice or crystal lattice. This is just like arranging bricks in an ordered arrangement to build a wall. So, a space lattice is an array of points showing how the constant particles are arranged at different sites in three-dimensional space. Having discussed all this, you should understand a few things. First, lattice points are purely mathematical concept, whereas atoms are physical objects. The absolute positions of the points of a lattice and hence the unit cells are arbitrary. The lines joining the lattice points are also imaginary. These are drawn simply to represent the three axes by which the relative positions of the points can be described. Second, the lattice points do not necessarily lie at the center of atoms or coincide with the unit cell vertices. Here, the first picture gives the three-dimensional periodic arrangement of atoms in the crystal. The second picture shows a corresponding space lattice. That is, by replacing each of the atoms with points, we got the space lattice. In this case, atoms lie at the same point as a space lattice. A unit cell has another important feature. It cannot assume all shapes. Why? Because a unit cell should have such a geometry that its replication fills the whole space. That means, when a unit cell is arranged periodically in space, there should not be any empty spaces or voids. So, which of these structures are possible for a unit cell? A cube, a sphere or a pentagon? Of course, a cube can be arranged in space without any voids. But what about a sphere and a pentagon? There will be voids. Hence, a unit cell can never assume a spherical shape or a pentagonal shape. Now, how do we characterize a unit cell? We have 6 parameters to characterize a unit cell, and these are called the unit cell parameters. These are the distances of the points along the axis indicated as A, B and C, and the angles between the axes indicated by alpha, beta and gamma. Let us understand these parameters. Let us take this vertex of the unit cell as the origin of the 3 axes. The distance of this lattice point from the origin along the x-axis is the unit cell parameter A. The distance of this lattice point from the origin along the y-axis is a parameter B. Similarly, the distance of lattice point along z-axis is a parameter C. Now let us check the angles. The angles between B and C is alpha. The angle between A and C is beta, and the angle between A and B is gamma. To describe a unit cell, we should know the unit cell parameters. The distances A, B and C gives the lengths of edges or the edge length of the unit cell. The angles alpha, beta, gamma gives the angles between the three imaginary axes. Now that you have understood the unit cell parameters, let us check which are the different types of unit cells. Crystals can have 4 types of unit cells. The first one is called simple or primitive unit cell. It is denoted by the capital letter P. Here, the atoms are present only at the corners of the unit cell. The second one is called the face-centered unit cell, denoted by the symbol F. Here, in addition to the atoms at the corners, atoms are also present at the center of each of the faces of the unit cell. The third type is called body-centered cubic unit cell. The letter used is I. Here, in addition to the atoms at the corners of the unit cell, there is an atom present at the center of the unit cell. And lastly, we have the end-centered unit cell, denoted by the symbol C. Here, in addition to the atoms at the corners of the unit cell, there are 2 atoms at the end faces of the unit cell. This is a simple cubic unit cell. It has atoms at all the corners. You know that a cube has 8 corners, and therefore there are 8 atoms in the simple cubic unit cell. Even though this is how you represent a unit cell, the actual arrangement of atoms are like this. The atoms are packed much more closely together. The atoms touches along the edges of the unit cell. Each corner of a cube, and hence each corner atom, is equally shared by 8 other unit cells. If we consider the part of the atom inside the unit cell, it can be seen that each atom at the corner contributes only 1/8 of its original volume to the unit cell. Hence, the contribution of the corner atom to the unit cell is 1/8. Since there are 8 such corner atoms in a unit cell, the number of atoms per simple cubic cell is 1/8 into 8 equals 1. In a body-centered unit cell, atoms are present at the corners. We have seen that the total contribution from the 8 corner atoms to the unit cell is 1/8 multiplied by 8, that is 1. In addition to this, there is an atom at the center of the unit cell, and this atom is not shared by any other unit cell. The whole part of this atom is completely inside the cell. Hence, its contribution to the unit cell is 1. Thus, the total number of atoms per a body-centered unit cell is 1/8 multiplied by 8 from corner atoms plus 1, that is from the body-centered atom, that is 2. Similarly, for a face-centered unit cell, there are atoms at the 8 corners which contribute a total of 1 atom to the unit cell. There are atoms at the face centers, and each of this is shared by 2 other unit cells. Hence, the contribution of the atom at the face center is only 1/2. Since there are 6 phases and hence 6 atoms at the face centers, the total contribution of the face centered atoms is equal to 6 multiplied by half, that is 3. Therefore, the total number of atoms per face centered cubic unit cell is 1 by 8 multiplied by 8, that is from the corner atoms, plus 6 multiplied by 1 by 2 from the face centered atoms. So, total 4 atoms. In an end-centered cubic unit cell, in addition to the corner atoms, there are atoms at the end faces. Atoms at the end faces are shared by 2 unit cells. Hence, the contribution is 1 by 2. Since there are 2 such end face atoms, the total contribution will be 2 multiplied by half equals 1. Thus, the total number of atoms present per an end-centered cubic unit cell is 1 plus 1 equals 2. Now, let us summarize what we have studied just now. Each corner atom in a cube is shared by 8 unit cells. A corner atom therefore contributes 1 by 8 to each unit cell. An atom at the edge of a cube is shared by 4 other unit cells. An edge atom contributes 1 by 4 to each unit cell. An atom on the face center of a cube is shared by 2 unit cells and therefore, it contributes 1 by 2 to each unit cell. An atom inside a cube is not shared at all. Now, let us try to solve a problem. Consider a crystal made up of 2 elements A and B, where A atoms occupy the 8 corners of the cube and B atoms are at the body center. What will be its formula? The trick to solve this is to find out the number of A atoms per unit cell and the number of B atoms per unit cell. In the question, it is given that A atoms occupy the corners of the cube. That is, all the 8 corners of the cube are filled by A atoms. We know that each corner atom contributes 1 by 8 to the unit cell. Therefore, the number of A atoms per unit cell will be equal to 1 by 8 multiplied by 8, that is 1. So, what will be the number of B atoms per unit cell? B atoms are at the body center. It is not shared by any other atom. So, its contribution is 1. So, we have calculated the number of A atoms per unit cell as 1 and the B atoms per unit cell as 1. So, the formula should be AB. Now, let us go back to the unit cell parameters that we have discussed earlier. You have understood that the unit cell parameters distinguish crystals from one another. Based on the unit cell parameters, crystals are grouped as crystal systems. There are 7 crystal systems. They are simple cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic and tetragonal. The unit cell parameters of each of the systems differ from one another. Say, if all the 3 unit cell distances A, B and C are equal and the angles alpha, beta and gamma all are equal to 90 degrees, it is called a cubic crystal. If the angles alpha, beta and gamma are equal to 90 degrees, but 2 unit cell distances A and B are equal to each other and C is different, then it is a tetragonal crystal. Each crystal system is specified by the shape and symmetry of the unit cell. You can see that the crystal systems range from the highly symmetrical cubic system to the highly unsymmetrical triclinic system. These 7 crystal systems are called the 7 basic crystal systems. We have studied that in the primitive unit cell, there are 8 lattice points and these 8 points are at the corners. There are different ways in which these 8 points can be arranged in 3-dimensional space and these are the 7 basic crystal systems that we have seen earlier. So, there are 7 primitive lattices. Adding further lattice points to the primitive cubic lattice, we get the face centered, body centered and end centered lattices. And these are called the centered lattices. Thus, there are 4 kinds of centerings. the 3 centered lattices and 1 primitive lattice. Since there are 7 crystal systems and each can have 4 kinds of centerings, there should be a total of 28 lattices. But Auguste Brevis, a mathematician, in 1848 showed that there are only 14 different ways in which similar points can be arranged in 3-dimensional space. His argument was purely based on geometry. That means the total number of space lattices belonging to all the 7 basic crystal systems is only 14. And these 14 lattices are called Brevis lattices. The 7 crystal systems with 4 kinds of centerings should give you 28 lattices. But Auguste Brevis proved that this is wrong and there are only 14 lattices. So, 28 minus 14 equal to 14 lattices are missing. Are you confused? You might be wondering why. The 7 crystal systems and the 4 kinds of centerings are shown here. You can say that some of the columns are missing. Exactly 14 of them are missing here. Only 14 lattices are shown. That is, for each kind of crystal systems, all kinds of centerings do not occur. This can be explained by considering the symmetry of the lattices. Symmetry considerations show that some of the lattice types can be mutually converted to each other. Therefore, they do not have a unique existence. Also, some of the lattice types are not compatible with the symmetry of the crystal systems. That is, considering the geometry and the symmetry of the lattices, there are only 14 different ways in which you can arrange similar points in 3-dimensional space. Or we can say that there are only 14 unique lattice types in 3 dimensions. These are called the 14 Brevis lattices. Here you can see all the 14 Brevis lattices, which include the 4 types of unit cells: primitive, face-centered, body-centered and end-centered unit cells, and also the 7 types of crystal systems. You have studied so much today. You studied that matter can exist in different physical states. One such state is a solid state. Solids have many unique properties that differentiate them from other states of matter. 2 types of solids exist: crystalline and amorphous solids. Each has their own unique features. Then you studied about the law of constancy of interfacial angles and its importance. Then you studied the crystal structure. You understood that a crystal structure is made up of lattice points and motifs. And an array of identical lattice points is called a space lattice. Hope you also remember that the lattice points are imaginary, but the atoms and the crystal structure are real. You also studied that the fundamental building block of a crystal lattice is a unit cell. And there are 4 kinds of cubic unit cells: simple cubic, body-centered cubic, face-centered cubic and end-centered unit cells. I trust that you remember the unit cell parameters which can characterize a unit cell. We also calculated the number of atoms per each of these unit cells. Then we discussed about the 7 crystal systems and the Brevis lattices. And there are 14 Brevis lattices. So that's all for today. See you soon.